All right, so today we're talking about statistical power. This is almost certainly the most difficult thing to understand conceptually in the course, and that's because you have to think backwards. And you have to assume you have knowledge that you literally don't have, which is a weird kind of thing. Thanks, Evan. That's a nice thing to say. Yeah, so we're gonna have to think backwards, which is wild, okay? You'll see what I mean in a second. And if you've looked through the slides, you'll know this already. We care a lot about type 1 error. That's the false positive, right? So that, in fact, we set the alpha level. All of our statistical techniques that we talk about in this kind of statistics, it involves setting an alpha level, saying if it's less than 0.05 or 0.1 or 0.01 or whatever, usually 0.05, that we say it's a significant difference. So we set it ourselves. That's something we do as researchers. In fact, our software, you look at SPSS or any other piece of software, gives you exact p-values. So it'll say p is less than 0.04132 or some such thing. Why is a type 1 error more important than a type 2 error? Because we make a really big point of this. We actually are given the probability of making a type 1 error in our outputs of our statistical software. Well, historically, it's partly to do with Fisher and his view of the null hypothesis. R.A. Fisher, the guy who developed the analysis of variance, which is called the F test after Fisher, also was a racist. Just thought I'd throw that out there. There's a lot of people who were kind of shitty. I'm just saying. He's good at stats. He was a really good biologist. First kin selection model. Also, and I don't mean like, you know how everybody was 100 years ago kind of thing, and you kind of go, okay, everybody was not like that. Enough that his friends were like, dude. All our methods are set up that way, which obviously it's a tautology. So anyway, Fisher thought that null hypothesis was a real thing rather than just a straw man you're trying to knock down. So he bought into this a little more than most people did, and he's very influential. But also, all our methods are set up that way. Now, that's, like I said, a tautology, because why are our methods set up that way? Because our methods are set up that way. That's not really a great answer, but they are set up that way, and it ingrains the thinking into us that type 1 errors are more important. So it's sort of a vicious circle is kind of the point I'm making here. And it's actually easier as a thought experiment, which a lot of this stuff starts out as, to set up a situation where nothing has happened, the null hypothesis. So I can say to you, we have two possibilities: something happened or nothing happened. Right? We have two things we can say: something happened or nothing happened. Well, when I say something happened, what something happened? Well, I have to specify something. When I say nothing happened, that's easy to imagine and easy to set up sort of theoretically, right? So for HA, we have to know how big the effect is. So we don't just have to know that there is an effect or what direction it's even in. We have to know how big an effect it is. How far apart are the two means? The sort of theoretical population mean and the obtained mean, or the mean between two groups or whatever. So you have to know a lot about the world and make a lot of assumptions. You don't have to make a lot of assumptions for the null. You just have to say nothing happened. That's an assumption, but it's not a huge one. When I say there's an alternative hypothesis that's true, that's great. Okay, what is it? Good. Now, how many points are the two groups different? And how big are the variances? I can specify all kinds of things that I just can't do easily. I can very easily say nothing happened. That's easy, right? So logically, it's a lot easier to look at the null hypothesis. So that's part of the reason. In the best of all possible worlds, we would minimize alpha, that's type 1 error probability, beta, that's the type 2 error probability, and that's the false negative, right? And we would increase power. Power is the probability of rejecting HO given HA is true. So given HA is true. We never know that. We can't know that. If we knew that HA was true or that HO was true, we wouldn't have to do the experiment. Right? We do the experiments. We do experiments. We do carry out research, collect data to find out how the universe works. If we already know how the universe works, some very small part of it, we don't have to do the freaking experiment, right? So in this case, in any case, we never know if HA is true. We make probabilistic statements that HO is true or HO is false. And if we say it's probably true that HO is false, then we just go, well, HA is the only thing left, right? That's the logic of this. All right. So let's look at this picture here. This is actually scanned from the textbook. I think an older version of the textbook, but it's from the same book, and he actually might still use the same diagram. So what I want you to do at first is simply imagine that this curve here, the H1 curve, isn't there. Okay, now that's not easy because it's there, but let's pretend it's not there, okay? So let's just say here's our HO, our null hypothesis distribution. Okay. It is a mean of u sub 0. It has a variance of standard deviation of sigma, variance of sigma squared. And if we get a mean greater than a certain amount, greater than the alpha, right? Or the alpha cutoff here at the critical value, we reject HO. So again, ignore the alternative hypothesis distribution. Just look at the null distribution. Are you with me so far? Any questions? So if it's bigger than this, if our obtained value is bigger than our critical value, which is going to be right here, this is in the rejection region, you call that, we reject HO, right? Okay. So actually, let's just go back for a second. So now let's look at H1. We never know that this is true or not, and we never know how far apart these are. But let's pretend we do. Okay, so let's pretend that we do, even though we can't. So that's why this stuff is hard, because we have to pretend we know things we don't know. And that's it's logically difficult to do. I mean, I find this very difficult to get my head around. I remember this is the part in stats where I would just sit there going, huh? And I did this a lot, my hand a lot. Now let's pretend H1 is true. We don't know this, but let's pretend it's true. Okay. We still make the cutoff at the same place. However, this is the distribution, H1, that's true. So we go here. There's a probability, all of this shaded area here from the cutoff version point, critical value, all the way over till infinitely negative over here, that we have the probability of getting a false null. Why is it, or a false rejection, like a false negative? Why is it false? Because I just said H1 is true in this case. So that's our probability of a type 2 error. And then this area here that's left over, that's our power. Okay, questions about that? Okay. Okay. So how do we increase the power? Now that was one of the questions on today's quiz, of course. Not nearly as what's the word I'm looking for? We weren't quite into it at the level we're getting into it today, obviously. Well, we could make alpha bigger. If we made alpha bigger, what if we just moved it over here? We moved it over. That would give us more power, right? Where's my pen? So look at this. If we made alpha bigger, so let's go back a bit again, so we get the. So let's say instead of alpha being here, where it is, we put it, here. Let's put it there. Now, there we go up to here. Oh, look, now power's here. Let's make it blue this time. Ooh, it's bigger. We have more power. That's pretty exciting. I mean, that's as exciting as the stuff gets, okay? So I'm just saying. So we could do that People don't like that very much for some reason. People seem obsessed with the 0.05 level, but we could make it bigger. Now, the downside is we get more false positives. And we talked the other day about how it would make sense to look for false in a public health thing. And I think I mentioned secondhand smoke research that almost never reaches 0.05, but all the research is in the same direction. And it's pretty clear it's bad for you. They can't all be false positives, even though they're all in the same direction. What if we could somehow move this distribution over? So in fact, instead of, let's see. Whoops, what am I doing? So now instead of H1 being here, let's just move it over to, well, what about here? What if we put it there? G now powers all the whole thing. Can we actually move? Can we actually move the distribution? Well, no, it's not something we can do. Theoretically, yes. But in reality, this is impossible to do. This is unlikely to do, making alpha bigger, because most people are obsessed with the 0.05 level of significance. We can't make this difference between these two distributions bigger. We can't. That's just a pipe dream. We mathematically can do it. They're just graphs. They don't know where they come from, but we don't work with just graphs. We work with actual data sets. We could decrease sigma. Oh, okay. Because if these things aren't as tight, sorry, are tighter together, these distributions, right? If they were tighter, there'd be less overlap. So we were not moving this. We're not changing alpha. All we're going to do is tighten these distributions up. So instead of being kind of fat like they are now, we just thin them out a bit, put them on a bit of a diet, a little bit of that keto, make them eat nothing but meat. I don't know, I'm just saying random things. I don't know what that extra dot's for. So this may be something we can do, decrease the spread. In fact, we can do. So making the variance smaller will tighten up the distribution. And at first you think, well, no, we can't do that because this is sigma and it is a parameter. We can't change parameters. We can only change statistics. However, the central limit theorem tells us that the sampling distribution of the mean has a variance sigma squared divided by n. And that's the thing we use. There's one thing we can do here. Okay, so we can take sigma squared. That's, what if we just make this bigger? So we take the, in other words, take the limit as n approaches infinity of that, and we get 0. In fact, at that point, there's no overlap, right? So we do have we can play with n. We can make n bigger. If n gets bigger, this whole quantity gets smaller. If that quantity gets smaller, it's easier to find a difference. And that's what this is about. Statistical power is the probability of rejecting a false null hypothesis. In other words, it's looking for an effect that is there, but you're not always going to find it. So what we can do, because sigma squared sub x bar is a function of n, because sigma squared sub x bar equals sigma squared over n, we just make n bigger. And that's something we can do. Collect more data. Right? This is why you get more statistical power when you have a bigger sample size. Okay. At some point, though, this is going to be a massive waste of time, right? And resources, because maybe going from 20 subjects to 30 is great, but going from, I don't know, 30 to 1,000, no, it's like, let's say going from 20 to 30 is great. Going from 30 to 40 might not be as helpful. In fact, it isn't as helpful. So we have to figure out what's the optimal size. What size do we want? What are we interested in? So let's circle back and look at what's called the effect size. So that's the difference between the two means, mu sub 1 and mu sub 0. That's all that is. So we have to standardize this because different things have different standard deviations, like there's less or more overlap. It can't just be difference between means. So we use what's called D. D is just well, again, it probably stands for difference. I don't know what it stands for. It's the effect size, and it's mu sub 1 minus mu sub 0 over sigma. Okay. Now we don't know sigma. We don't even know these. We have to make some guesses here, everybody. We have to really make some guesses here. So how are we going to attack this? All right. Well, there's got to be a way, or the course would stop now. Well, one way we can do this is prior research. So you can just look around and say, okay, how big are effects usually in this kind of research? And in fact, one of the first things you should do when you're, well, one of the first things, but once you're designing an experiment, one of the things you have to do is look at the old literature, obviously, but you should look at the kind of data they collect and see, okay, how many participants do they have? What is the size of the average difference when they use a certain rating scale or whatever you're using? So you could use prior research. The question you have to ask yourself is, how big an effect is big enough? Just a second here, my chair's all buggered. Okay, so the thing is, God, it's hard for me to sit still. I'll tell you, we're going to be live and in person next week. By the way, I think our classroom is EW206. That's just been listed. I'll also tell you that I do not look forward. I do look forward to not having to sit on a chair. I fidget a lot. Anyway, how big is big enough? There's a difference between statistical significance and practical significance. So almost any variable will show difference between two groups. We're psychologists. We are dealing with a very complicated science looking at complicated things, nervous systems. It can be in people or in other animals, but behavior is complicated. And it has multiple causes. Very rarely do we have just one thing causes one thing. Okay. So at some point, almost any variable will have an effect between two groups if the groups are big enough. There is probably a difference in the average. I'm going to pick something really odd here that I don't know anything about, but there's probably a difference in the average size of the toenail on your pinky toe between psychology students and sociology students. I don't know why that would be or what direction it would go in, but I would put money down that if we collected 10,000 psych majors and 10,000 sociology majors, there would be some weird difference. I don't know why the difference exists, but if we had 10,000 people, we probably get a significant effect. Is that meaningful in any way? No, not at all. In fact, but I bet you'd find something. I really do, because we're dealing with something very complicated. Living systems are complicated. And let's turn it into behavior. A list of words that you remember, and it's 20 words, and we're gonna use the same 20 words. We have 10,000 psych students and 10,000, let's change it up, biology students. There's going to be a difference in memory between the two groups. It's going to be so small as to be meaningless, but maybe you have 10,000, 15,000, even 1,000 people. It shows up as statistically significant, but it's like 0.1 word difference on, say, a 10-word list. Is that meaningful? No. There's some small reason that has to do with what major you choose, maybe. So how big is big enough? I often say to my honors students when we're, in fact, I've said it to all three of them this year, when we're dealing with collecting data, we're designing their experiments, and they say, how many subjects do I need? And I say, if it doesn't show up with 15 people per group, I don't care. That's my personal thing, and you'll see why in a second. But if there's no difference between two groups of 15 that are randomly selected and randomly assigned, who cares? It doesn't really matter a great deal. Right? Okay, so practical and statistical significance are a different thing. So how big is big enough? I don't know. Well, a guy named Cohen came up with an idea. And he has classified these things as follows. What he called a small difference, which is a D of 0.2. Now, just to remind you, I'm just going to write this up here just to remind you what D is. Whoops, there we go. D equals mu1 minus mu0 over sigma. Okay, that's just so keep that in mind. So that's what D is, okay? So it's a small d. That's when this thing is only 0.2. That's very small, isn't it? In fact, there is 85% overlap between between mu sub 1 and mu sub 0 distributions. The medium one, and this is the one most people use when they do these power calculations, there's still 2/3 of those two graphs overlap. A large difference, there's still 53% overlap. That's 0.8. Okay. Okay, so who cares? Now what? I guess, and that's a reasonable question. We combine this information with the effective sample size. Now this is where it gets, this gets a little, we have to make some, there's going to be some steps here. And this is where it gets a little complicated. So there's something called the delta statistic. That's a delta. Okay. Oh, delta has a whole new meaning now. Happily, there's no Omicron statistic we have to deal with. Okay, what's delta? Delta equals D, that's that difference measure. And we're just going to pick one out of the air from Cohen's thing. And we're probably just going to pick 0.5. That's what most people do. Times how the times f at n. What does that mean? That means how is the measure of error you're using? That's going to be either standard deviation or variance. With t-test, it's going to be standard deviation. How is it affected by n? Well, f at n, yeah, is how it's affected by given test. So for a t-test, f at n equals, and I didn't have a square root sign available with the regular font. So that means square root of n. It's not check mark n bar. So it's the square root of n, okay? So f at n is how n affects a given test. So for a t-test, f at n equals the square root of n. Just take a look at the t formula. Straight ahead vanilla t. Okay. How n affects a test? Well, look, square root of n. That's how n affects a test. Okay, so it's square root of n. For something else, for something that uses variance, like analysis of variance, it's just going to be n. But right now, we're using t-test, so it's going to be the square root of n. Okay? All right. This actually isn't that bad. It's just a weird way of doing things. So if you know D, notice I got this in quotes because you don't know it. You don't know it. But you've said, I'm interested in an effect. The minimum size will be 0.5. 0.5, we still have 67. Was that right? 67% overlap. Just want to double check that. There we go. Yes, 67% overlap. That means 2/3 of the distribution for the null is the same as the distribution for the alternative hypothesis. And in fact, if I looked at, let's see if I can draw that. So that's going to look like, whoops, let's delete all that. So we got, so 67%. Here's the null. I'm not usually very good at this, so let's hope I can do a decent job this time. There's your null hypothesis. 67% is 2/3. Oh, good. Somebody's on the phone. That's not 2/3 overlap. That's only what? Maybe 40%. 2/3 is probably something like that. Holy jumping. Yeah, that's 2/3. It's not bad. It's probably a little less than 2/3, but that's how close these two distributions are. And that's the gold standard people use a lot in psychology to say there's a difference between two groups, to say that we're interested in a difference that big. That's not a huge difference between two groups, is it? Okay. Let's keep going forward here. Right. Oops, my damn thing does a thing. There you go. So if you know D, you can figure out the sample size for a given power. So let's say we know that D is 0.5. In other words, 67%, 0.67 overlap, which is just a massive overlap, but let's just say. You usually pick 0.5. Anything under 0.5, most people would say that may be statistically significant, but it's practically meaningless. Like I was talking about with the idea of finding differences in big toe sizes between, I don't know, sociologists and psychologists. Okay. So let's say we got a power of 0.8. We'd like there to be an 80% chance that if there's a difference, we find it. Remember, power is the probability of rejecting a false null hypothesis. So if there is a difference, we want to find it. So we're just, notice what I'm doing here is I'm just setting things. We just set alpha. So we're saying D is going to be 0.5. Power is going to be 0.8. And there's an appendix in your book, and it's called power. Okay. You can also do this. There are online calculators for it. And that's the way I think most people would do it today. I'm trying to show you the logic of doing this. And again, there's another one of those empty orphan dots. I don't know what that's there for. Little Orphan Dot. It's a great play. It's a musical. That would be Little Orphan Annie. Anyway, really, you're just using another table. So D is 0.5. 1 minus B is going to be 0.8. That's, again, that's the difference. We have picked that out of the air. We have just said 0.5. And that's what most people would use. I would encourage you to use maybe something a bit bigger, but 0.5 is kind of a standard thing. 1 minus beta, 0.8, that's good. So there's an 80% chance if there's a difference in this experiment, we will find it. I mean, there's a 20% chance we won't. But you know what? Missing a difference that's there isn't a big deal because someone else will find it. It may be bad for your career, but it doesn't really affect it doesn't affect, statistically, you're not going to at least, just because you miss something, somebody else will find it. So science marches on, is what I'm saying. Alpha is going to be 0.05 because alpha is always 0.05 for reasons that are completely bizarre. And we've already talked about, but that's probably what we're going to do. Here's the table. So here's the table, right? This is literally scanned directly from the book. And this is one of the few cases where I'm going to say that's actually better that we're doing this like this rather than in a classroom. Because frankly, this looks like crap on a screen, whereas it looks decent on your screen and it will look decent on the YouTube video that is coming. Okay, so D is 0.5. Here's our alpha, that's 0.05. And there, oh, look, there's D. 0.5. You just look it up in the table. So, sorry, yeah, D is 0.5. 1 minus beta is 0.8. And that is the D. And what we're going to do, let's get rid of that. Get rid of all those. Let's zoom in. Let's move this over a bit. Now, so you can see now what we're going to do is we're going to find out what the value is that we're looking for. Okay. So we're going down this column here. Let's just go back for a sec. So D.5, 1 minus beta 0.8, alpha 0.05. So look at the table again. There's the alpha, 0.05. Okay. There's the D. Sorry, that's the delta. I knew I was making a mistake. Okay. 0.8. There's the power we're looking for. And then we find the delta is 2.8. So we're going to zoom in. Do that again. 0.05. That's this column. And then 0.8 power, we just read here, and then we go here. It's 2.8. It's right there. It's a very easy table to use. So now we just do some math. Remember this whole thing. Now, where did I get n equals delta over d? All I did is I went back and I'm going to go back again just to remind you. Okay. Here it says delta equals d times f at n. All I'm doing here is I'm going to solve for n. So I'm going to isolate the n. I'm going to isolate the n. So delta equals d times f at n. Delta equals d times square root of n. Right? Keep going. Let's go back to where we were. And there's our table. Again, we look it up. We get 2.8. delta equals then, if we, so remember it's 2.8, we read from the table, n, because we're trying to find n, equals delta divided by d, and we had a square root in there, so I squared it, right, to get rid of the square root. So delta over d squared equals n. 2.8 we got from a table, 0.5 we got from thin air. We said 0.5 was good enough, and we square that and equals 31.36. So what that means is, let's go back, we need 32 people in an experiment that has a power of 0.8 and an alpha level of 0.05 and a D of 0.5. We need 32 people to find a difference with that power and that level. That's really all this is. It's really just plugging something into a different formula. Now, again, you would nowadays you can just look something up on the web. There are calculators for these things. What if we want to increase the power? Let's say we want to go from, this is the point I was making before, there's sort of diminishing returns here. We want to go from, let's make our power 0.99 instead of 0.8. 0.99 instead of 0.8.
No, I was just putting it the coffee pot for you.
So you can also see there's also a very big discussion about coffee going on in my kitchen. 0.99 instead of 0.8. The delta value now from the table is 4.20. 420. So it's 4.20. So n equals delta divided by d, 4.2 divided by 0.5. We square that. Suddenly now to go from 80 to 0.99, we now need 72 people. We have to basically double more than double our sample size to just go up by by what? 25%, basically, almost 25%. Is it worth doing that? Probably not. That's why you don't see experiments with that many people. It seems crazy. Like you're not getting that much extra bang for the buck, right? Collecting data is time consuming. As I've said to my honor students before, it's, to quote Principal Skinner on The Simpsons, science has all the excitement of sitting still, paying attention, and writing down numbers. And that's a thing here. This is really doubling your sample size to get that small bump in power. I wouldn't say it would be worth it. You might ask yourself, what the hell is delta? It's called the non-centrality parameter. This is more just for interest sake. People ask, I didn't used to have this slide in this presentation, but then people said, what's delta? So now I'm going to tell you what it is. Because and by the way, I was always the guy in stats class going, yeah, but what does it mean? So I was the annoying guy that said that. So we assume HO, right? We make the assumption that HO is true. And under HO, the expected value of T is 0. Why is that? That's because there is no effect. So X bar minus mu, X bar should be the same as mu. So it should be 0 if there's no effect, right? So how likely is it that we find a value of delta that is greater than the critical T value at 0.05? And that's all this is. So you see what delta is? It's actually just, it's the same as the T statistic, except it says it's the expected value is not 0. That's all it is. I wouldn't, if you don't care about this, I wouldn't get too worked up about it. The important point about all of this discussion is you should do power calculations, and they don't have to be, as you can see, it involves looking stuff up in a table, and all the values are filled in. Like you pick delta, sorry, you pick D, you pick alpha, and then you find out what the delta is for that, and then you just find the n. Now, a lot of times it's going to be something like around 30. This is why you see a lot of people using about 30 subjects in experiments, because that gives them a 0.8 power with a 0.5 effect size. Okay. So either do the calculations or go to an online tool that shows you statistical power for an experiment. What they'll do is they'll ask you how big an effect you want, and they'll ask you what your alpha level is and what statistical procedure you're using, and it'll just spit it out for you. It's not hard to do. It's totally doable, and you can save yourself extra work Like you can save yourself like, oh, I don't think I need 50 people, 30 will do or whatever. And it'll also, it saves you not only extra work, but it saves you not doing too much extra work, because getting that extra 70 or 80 people doesn't really help you a lot. It just doesn't help. All right. Questions on this stuff? Any questions? You've been very silent today.
I have a question.
I have answers.
Just, it was kind of hard to see the graph. We find the 0.8 power under the alpha 0.05. That's where that comes from?
Yep. So the delta part, I wonder if I can probably pull this up here. Let's see if I can. Okay. Come on, go away. We're gonna just take you. I'm gonna see if I can switch to the camera from my phone, which I should be able to do. I gotta find it. There we go. And then I've got to go like, we're gonna kill that share. And then we go to, we change camera. No, we're gonna do it like this. And advanced, let's see if I can do this here. Yep, from the second camera. Should work. It does. Okay, maybe you can see that a bit better. So now I have to follow along. 0.05, there's the column. We wanted a 0.8 power. Let's keep going till we get to 0.8. Right there. We go over here and it's 2.8. Whoops. So that's the delta value. And then we just throw that into the, so we pull up this value. I'm going to use my stylus here because it's with my finger, it's harder. So we start up here, 0.05. We go down here till we get the power we're interested in, which is 0.8. There it is right there. And then 2.8 is the delta value. And then we just sub that back in to the, that's what I'm looking for. Yeah, we just sub that back into the formula, which is n equals delta square, equals delta over d, and we square it. And the d, we already know it's 0.5.
Okay, thank you. That makes a lot more sense. I think
Yeah,
I'm just getting confused.
No,
D
believe me.
staying for delta, but it doesn't.
Yeah, believe me, it's one of these things that there's a few hard things about this. And one of them is we aren't used to just things to almost pulling everything out of our heads or a table. Usually something is something we have to calculate, not just the final answer. Whereas with doing, when you do these power calculations, you literally are making everything up. And that's why this is kind of a dark art. It's the math is completely solid behind it. But saying, I'm interested in the difference this big is really completely arbitrary. It's more arbitrary. It's almost more arbitrary than the 0.05 level of significance. But yeah, no, thanks for the question. Other questions? What do you got? I want to see. I see the chat has something in it. I just don't see what it says. I'm going to zoom in now. Yes, this is certainly fair game for the test. Yes. Yep.
Will D always be 0.5?
D, it's up to you. 0.5 is probably the smallest one you'd be interested in. 0.5 is the smallest, is what most people would start out with. One of the things you can do though, Rina, is you can actually go into the old literature and take a look and see how big is the difference people normally find. So if the difference people normally find is, and the way you calculate this is you see the two means, divide by their standard deviation they got, and it tells you how big the effect size is. You just do a quick calculation. And if the effect size people normally find is 0.9, use that. If the effect size that everybody finds is 0.2, I question if it's practically significant, but if it's always 0.2 and always in the same direction, that's what everybody's going with, use that. But if you don't know, 0.5 is a good starting point. That's a really good question. Anything else? Other questions?
I just wanted to clarify, when it says mu1, that's just interchangeable for A, right?
Yep.
Okay, cool. Thanks.
Yep. Yep. And if you have two groups, if you're like, I've shown you this all with one group, right? Because it just makes the example easier. If it's two groups, it's still the difference between those two groups that you're interested in. And then what the standard deviation of that difference is. So it's always what the bottom of a t-test would look like. This is one of the reasons it's important to know how to do these statistics, because to do power calculations, you actually have to know how to do statistics. Well, actually, you can just look stuff up on the internet, but it's better if you do it that way. But yeah, and you're usually going to choose 0.5. Other questions? So practically, the only way we can increase power is by increasing n. We can increase power by increasing the difference between two groups, right? But we can't really do that. That's not something we have the power to do, because that involves godlike powers of changing population distributions. But mathematically, the numbers don't know where they come from. We could change the standard deviation of the difference. I'm sorry, that's where we want to get to. We could change the alpha, but usually we can't do that because the powers that be, the man, is telling us we have to always use 0.05. So we usually can't do that. The only thing we can change is the overlap. And the way we do that is by increasing the number of observations. So I was to ask you, how do you increase the power of, is it possible to increase the power of a test, and how do you do it? It's not really possible. We can only guess. Because to know the power of a test, we have to know things about the population, and we can't know those things. So this is an estimate. A lot of statistics is just estimates, really. So we can't really know the power of a test without having supernatural powers. But the math doesn't know that. So what we could do, we can do a whole bunch of things. We can change the difference between two means. We can change the size of alpha, but we can't really do those things. What we can do is increase the number of observations. And that's the key stuff to take home from this today. And that you should do these calculations, or do some, or at least think about power to the point of looking something up using an online tool, rather than just guessing and saying, I need 30, I need 50. You don't necessarily need that many, or maybe you do. Any other cues? Okay. Well, that seems pretty good. Right. So we'll pack this in for today.